section 5.4, part 2. Here we go. This is all about the application of trig functions. Here's where your real-life applications are going to come from, for those of you looking into your project already. This is going to be the last section we are likely going to cover in Pre-Calc 12. I don't know whether you should be excited about that or not. Maybe. Possibly. Unless I can somehow figure out how to make the course a little bit shorter and I can squeeze in chapter 6 because it's got one of my favorite sections in it. But who knows? Maybe at some point we'll get to that, maybe not. For the year that I'm creating this, this is your last section. What are the purposes for today? We got two of them. So we got use trig functions to solve word problems and solve equations involving trig functions. Nothing really new. A little bit. It'll be fun. So, a reminder. I reminded you about this last class, but I'm going to remind you about it again. Remember, with our 4 quadrants, we have very specific equations once we have the reference angle. So, once we have a reference angle and we know what quadrant we're in, we need to deal with these equations, memorize them, know them, tattoo them on your arms if you really want to. But you'll need to know this. Actually, don't tattoo it on your arm because then that's going to be cheating for the test. And then, I don't know, we'll have to do something about that. Let's solve some word problems. So we've got the height of a piston in a cylinder at t seconds is given by this equation. So h equals 2.5 sine 2 pi over 0.5 or 0.05 time plus 12. We've got a whole whack of things we can solve with this one. First, we want to know what's the maximum height. Well, we know the A, B, C, D values for this equation. Maximum height is given by D plus A. So my vertical displacement plus the amplitude, so 12 plus 2.5 because it's 14.5 centimeters. I don't know how you would have known it's centimeters because I didn't tell you it's centimeters, but it's centimeters. Next, what is the minimum height? Same equation, except minus the amplitude. 12 minus 2.5 is 9.5. Those ones are pretty straightforward. What is the period? Period's also really easy to find. Since we know this, it's 2 pi divided by whatever the b value is. Since there's already a 2 pi in there, it's just going to be 0.05. You can plug it in your calculator, try it if you want. Frequency, I don't know if we've talked about frequency before. Frequency is just 1 over the period, which you have already. So you can just plug that in, and it's 20 revolutions per second. Pretty fast for a cylinder, or piston in a cylinder. D is asking what is the height of the piston at 8 seconds. So this one's the easy number to plug in. Just plug in 8 for time in our equation. Plug that in your calculator. Your height is 12. Fairly straightforward. It's just you're at your midpoint. And then E. So E is the question that we were dealing with last lesson. So at what time is the height of the piston 10 centimeters? So we set up our equation like this, and this would have been what I gave you yesterday. So this would have been, or last lesson, if there's a weekend in there. This would have been the equation I would have given you. I wouldn't have put it in a word problem. But this we've solved already. We need to do some algebra. Isolate sine 2 pi over 0.05 time, or 0.5 times time. So we subtract 12. Divide by 2.5, we get this. Remember, we only use the positive values. Because we're trying to get our reference point, we need positive values. So when I do the inverse sine at this point, I need to make it positive 0.8 instead of negative 0.8. So we get this. That gives us 0.927. We're dealing with radians. Make sure your calculator's in radians. And here we go. This is our expression. This is again the reference. I want to know specifically in what quadrant we're in. So sine being negative puts us into quadrant 3 and quadrant 4. Quadrant 3 is going to be our pi plus the reference point. So we take our equation that we had there, we go pi plus the right-hand side of the equation, and then we solve for time. So minus pi, divide by that fraction there, we get that t equals negative 0.0176. This is a problem. Why is it a problem? Well, we can't have negative time. We're not going to travel backwards in time. So we need the first positive time value, which means I just need a coterminal angle. So I take this time and add to it the period. We already figured out the period. That was part C, I believe, in this question, which was 0.05. So we add that value, we get t equals 0.032. There we go. This is the positive time for quadrant 3. Let's do the same for quadrant 4. So we take this 0.927 equals 2 pi over 0.05 times time, and we take 2 pi minus the right-hand side of that equation. We'll be in quadrant 4. Solve for t. We minus 2 pi, get rid of that fraction. Time is 0.043. This is positive, which is good. So we just use that value. So therefore, time is these two values. So those are the times at which the piston will be at a height of 10 centimeters. Let's do another one. So on one day at a seaport, a high tide of 9.4 meters is first reached at 9 a.m. If the next low tide of 2.6 meters occurs 6.2 hours later, we want to determine a couple of things. First thing we want to determine is the height of the tide at 4:30 p.m. So before we can actually solve this, we need to make an equation. So that's where we're going to start, is by making an equation. Let's pick out what we can find from the question first. I just said that. Oh yeah, a couple of assumptions. First, we're going to use a 24-hour clock, because otherwise it's going to be a little bit confusing. And with the 24-hour clock, we're going to assume midnight to be 000. Just to say that that's our starting point is at midnight, and then we move forward from there. This is important information so that we can determine our phase shift, because we need to know when's the 0 point. Instead of midnight being at the end, that's at the beginning, which is actually the same thing since it's cyclical, but I digress. So what we know is that the high tide is at 9.4, the minimum is 2.6, that's given in the question. We are told that to go, first we need the D value. Since we know max and min, we can figure that out. That's first point. We know the A value. Again, this is just max plus min divided by 2. Max minus min gives you, those are your D and A values. We are going to assume that this graph is a cosine graph because we're given max and min values. We have, because that tells us where our starting point is. Cosine always starts at a max, or if we have a vertical reflection, it starts at a min. So it's easier to deal with cosine instead of, we could figure it out from sine, it's just a little bit messier. We know C equals 7, so my phase shift is 7 since we are told the high point is reached at 7 a.m. That tells us how much our phase shift, our maximum value, shifts over 7. So the time it takes us to go from the maximum to the minimum was 6.2. That's half a rotation. So if I want to know from max to min and back up to max, I just double that. We get 12.4. Since that is the period, it's 12.4, we can figure out the B value. It's just 2 pi divided by the period. Now I've got everything, A, B, C, and D. I can make my nice and fabulous equation. It looks like this. So H being our height of the tide, is equal to 3.4 cos 2 pi over 12.4 times t minus 7, all plus 6. That was just the beginning. We haven't even solved the question yet. So now we can look at the question. We want the height of the tide at 4:30 p.m. First, we need to figure out 4:30 p.m. is at what time? So we're using the 24-hour clock. Time is in hours, so we need to figure out where we are with that. 4:30 p.m. is 16.5 hours beyond midnight. If you're unsure where that comes from, come talk to me during class. I can explain that to you. But this is just using a 24-hour clock. 4 p.m. is 16 o'clock in 24-hour time. Now I can take that, plug it in for t, solve for it. We get that the height is 6.34 meters. There's your height at that given time. Second thing we want to determine is when the tides are at 5 meters. So this, we're told the height, we now need the time. So plug this into our equation, we get this. This should look very familiar by now. Hopefully you're starting to get comfortable with solving some question that looks like this. First step, isolate my trig variable, or my trig function, not the variable. So I need cos of this big bracket thingy. We need to isolate that. First we subtract 6, divide by 3.4. Now we have isolated cosine. You'll notice that this cosine ratio is negative. Just like I've told you many times before, I need to get the positive value to determine my reference point. So I'll do the inverse cos of positive 0.29. That left-hand side we can plug into the calculator. We get 1.27. Okay. Now we take this and we need to go into our different quadrants. So cosine is negative, cosine is x, negative x values give you quadrant 2 and quadrant 3. Now we take our equation at the bottom left and we need to adapt it into quadrant 2 and quadrant 3. Quadrant 2, pi minus the innards of the cosine there. So on the right hand side it's pi minus all of that stuff. And then solve for t. Minus pi, divide by that ugly fraction, add 7, there you go. Time equals 10.69 hours. Pretty straightforward. I need this in terms of hours, minutes, seconds, because I want to give it as a timestamp. We had 4:30 as the last one. I need to figure out the exact number. So 10.69 hours. The whole number 10 is the amount of hours we're at. So it's 10 a.m. We now need to figure out how many minutes and how many seconds. So I take the decimal part, 0.69, and I turn this into minutes by timesing it by 60 minutes over 1 hour. This gives us 41.6177 minutes. I'm going to take the whole number. So we've got 10 hours. We've got 41 minutes. Now we need the seconds. So 0.6177, so that much of a minute. I need to figure out how many seconds that is. Take that decimal, times it by 60 seconds over 1. This gives us 37.061 seconds. So my overall time is 10 hours, 41 minutes, 37 seconds. So this is the time that we get. 10:41 with 37 seconds a.m. That's how precise we can get with this. Now with this, you'll notice that we have lots of rounding that we did in the middle. You need to be as accurate as possible. So when I solved this with the numbers, I did not round from the point we started in quadrant 2. So I took the exact value of 1.27 and I kept that value as exact when I did the whole calculation. So I did not round it till the very end. This, I will be a little bit lenient with this. You will end up being a couple minutes off or a bunch of seconds off if you round earlier or later. So just try to not round whenever possible so that you can try and be as exact as possible. Let's do this again for quadrant 3. So we start with our equation that's at the very bottom left corner, the 1.27 equals, and we will convert this into quadrant 3, which means the right-hand side is pi plus what we originally started with. Again, solve for t. Minus pi, divide by fraction, add 7. Here's our time, 3.31 hours. So it's going to be 3 a.m. is when we are going to start. We now need to figure out the minutes and the seconds. So 0.31, this is our second half, that part of a fraction of an hour, times it by 60 minutes over an hour, we get 18.38 minutes. So 18 minutes. Now we need to figure out how many seconds. So I've got 0.38 of a minute, gives us 22.939 seconds. So my overall time, I take the whole numbers. The original is 3 hours, 18 minutes, 23 seconds. I can round that seconds up. These are the 2 times that the tide is at 5 meters. Now for this, it didn't give me a domain. It didn't say between this time and this time. We're just going to assume a 24-hour period. And these are going to be my 2 times that I'm in 5 meters. We've got one more question. So this one's not a word problem, but this is a tricky enough equation that I wanted to run through this. This is essentially last lesson with a slightly more difficult equation, but my method is all the same. And you've seen this method over and over and over and over and over and over and over again. So by now, it's hopefully starting to at least sink in a little bit. My process for this is always the same. I need to isolate sine. Then I need to get my reference point. Then I need to figure out what quadrant I'm in, solve for x, get all the values in the range, or figure out that general solution. So this one, let's algebra. So I subtracted 14.6 divided by negative 2.8. That algebra you've seen before. I've got sine, all this stuff equals negative, so I want to use the positive value. I've done all the examples having to flip to positive so that you can see it many, many times so that hopefully you can remember that. So I have the inverse sine of the positive value of this. Then we need to plug that in the calculator. We get this. Pi over 4 times x minus 6 equals pi over 6. This is my reference point. Sine is negative when we're dealing in quadrant 3, quadrant 4. We need to take this equation, adapt it. So the pi over 4 times x minus 6, this was our part that was inside the sine function. That's the one we need to adjust. So in quadrant 3, it's pi plus that side. We're going to solve for x. So subtract pi, divided by pi over 4, add 6. Here we go. X equals 8 over 3. Now, this is a decimal. You could write it as a decimal, but we always want exact numbers when possible. This is exact. Leave it as is. Don't touch it. Now we look at quadrant 4. Do a little bit of algebra. Hopefully you can see this by yourself. I don't need to tell you what it is. And we get that x is 40 over 3. 40 over 3, if you were to actually calculate that out, is bigger than 2 pi. So we've got a problem. This is too big to fit into our domain. So we need to figure out what's a coterminal angle to this, which means we need the period. We have the b value. Period's pretty straightforward. Just 2 pi over that b value gives us 8. 8 is our period. So going back to quadrant 4, let's subtract 8 so we can get a value that's within our domain. 16 over 3, that is in our domain. So my solution to this is x equals 8 over 3 and 16 over 3. Again, you can test this out. You can add or subtract 8 onto these values of x and see if I get lower than 0 or above 2 pi, just to verify where we're at for that. And there you go. That is the end of chapter 5. We have seen a lot of examples of solving equations that we just did in that last example. As you can hopefully see with that and recognize with the pattern's the same. We're always doing the same steps, even though those equations look ugly. As long as you can do the exact same process, the exact same steps, you will do just fine, no matter how complicated those values get. Time for the last movie that is very poorly described. This next one you're going to have to put on your thinking caps. You'll need to try and figure this one out. So this movie has basically no real dialogue except for the humans. The humans talk normal, but the rest of the individuals in this movie only say their names, but they say it with emotion, so you can tell what they're trying to say. So if you think you have a guess for this, let me know in class, and I will see you then.